Uh, Thank you very much. I'm Toru Kouyama. I'm from Japan. And also I'm a member of Akatsuki member. So I'd like to introduce recent result from Akatsuki observation, especially from the LIR thermal sensor. And this time that I said a long time, but I'm sorry, this is not the meaning of geological time scale of long term, not a million or billion years, just a scale of mission. So 10 or 5-year scale, I would like to say. Anyway, in this talk, I would like to show some results from Akatsuki 10-year observation, 7-year observation. Okay, as introduction, I'm recent years, I'm interested in long-term variation, 5 or 10-year variation in Venus and atmosphere, which is confirmed, which we can confirm this in Venus Express and the Akatsuki observation data. As you see, this is a result of observing UV albedo. Horizontal indicates the year and vertical is the UV albedo. And if the number is high, that means the Venus is more bright. And if the number is low, Venus is rather darker. As you see, there could be something like this kind of variation, 10-year scale variation. Interestingly, this kind of time scale variation can be seen in the zonal wind speed. This kind of variation are recently reported also in the Katsunzev et al. 2022. Which should be the 11 or 12-year cycle. Anyway, in Venus and atmosphere, there should be a 10-year scale variation, not only the UV albedo, but also in zonal wind speed. And if, as you see, if the UV albedo change, that may induce the solar heating variation. And if the solar heating variation happen, then maybe the balance of atmosphere would be changed, then which may cause this kind of zonal wind speed variation. I think based on this kind of idea, Lee et al., Yeonjun, and also Sebastian examined how this kind of situation happened. In their GCM experiment, they changed their solar heating rate, they change the solar heating from maximum to minimum. The amount of variation is around 40%. And according to the changing solar heating in their experiment, the solar heating getting decreased. Then following to this solar heating variation, temperature and also zonal wind speed decreased. And this is the result. And as I said, there are results about UV albedo and zonal wind speed, but still we do not have the result about temperature. So we think temperature is now still a missing parameter. So it is worth to investigate how about the temperature for concerning this kind of long-term variation. Fortunately, we have Akatsuki, we have LIR, which is a thermal sensor. So we can get the temperature information from this LIR data. And Akatsuki is observing the Venus since its Venus orbital insertion operation at December 7 in 2015. And now still Akatsuki is working well. And also, fortunately, LIR is also working well. And here is data from LIR. This is the first image of LIR after the Venus orbital insertion. And this is a recent image. And basically, LIR team believe the performance LIR is same as first view. I mean, as you see, we can see the clear for a hot region. And also, we can see the clear colder surrounding region. So that means the LIR can resolve the temperature difference on the Venus disk. Anyway, so by using this data, I checked how such the long-term variation can be seen in the temperature. So this is the purpose of this study. I would like to investigate the long-term variation in temperature by using LIR data to illustrate more concrete characteristics of Venus atmosphere. And I would like to discuss how such variation, why such variation occur. Okay, but before going to showing the results, I have to say the actual performance of LIR. Although I said performance of LIR is good, but we found there is a calibration issue, of course, to see the long-term variation. The one of the big calibration issue is, as you see, we found there is a gradual temperature increasing when we see, for instance, a background temperature. The temperature increasing is around 20 Kelvin during the mission. Also, this kind of increasing is seen in the Venus and disk temperature. As you see, we think this gradual increasing is due to the most likely to the calibration issue. And actually, we have some evidence this is due to the calibration issue, and especially this is due to the sensitivity degradation. We have concluded, and so I don't explain detail here because of time, but we think there should be the 1% per year sensitivity degradation happen in the LIR, and by considering this sensitivity degradation, we successfully cancel the temperature increasing both in background temperature and also Venus temperature, as you see. So we believe this is not a natural, just a calibration issue, this temperature increasing. By applying the calibration procedure, we successfully cancel the temperature increasing. So we think this is actual temperature of Venus during the Akatsuki mission. Okay, I have to say, recently we almost finalized our calibration procedure. So we want to release new version of recalibrated LIR soon. Now the paper is under review, but we already finished the internal version. So we want to release this new version soon. Anyway, so okay, this is a result from LIR data. In this plot, horizontal is days since VOI, Venus orbital insertion of Akatsuki, and the vertical represents the observed temperature. And as you see, there are a lot of up and down peaks. Actually, this is due to the thermal tides at the cloud top level. Actually, most significant component is thermal tides, but in this study, the thermal tides is not the main target. So I cancel the component of thermal tides by subtracting their, how can I say, their fluctuation due to the thermal tides in my data analysis. And as you see, more, how can I say, it is easy to see more long-term variation, I think. And actually, by performing the periodical analysis, I found there should be the scale of 2000-day perturbation. Although I don't want to say here this variation is a periodical one. I do not think, but I do not think this is necessary to the periodical one. But if we want to know time scale, I performed this periodical analysis, and I found a good long-term trend like this. And interestingly, there could be the sub-trend, sub-peak here, 800 days. Anyway, interestingly, this kind of long-term variation, 2000-day perturbation, can be seen also in the zonal wind speed. This plot shows the result from cloud tracking. That means the zonal wind speed. And this is a 280, I think 6 nanometer result. And also, this similar period can be seen in the another band of UBI. So there could be this kind of long-term variation both in the zonal wind speed from the two filters of UBI. Anyway, as I said, there is a long-term variation with a period of 2000 days in LIR, also in UBI. And then I compared them like this. And also interestingly, the phase of the variation is almost same. That means the temperature and the zonal wind speed show the correlation. It correlates up and down. And actually, the period is almost same. And also the subpeak is almost, there are common peaks at here, 800 days. I don't know why, but maybe the temperature and zonal wind speed varies commonly. There should be the strong correlation between the zonal wind speed and the temperature. And also, I want to say, here is a 100-day lag. I mean, zonal wind speed varies earlier than the temperature. It's also another thing I found from our data. And so my target is actually not only seeing the long-term variation, but also I want to discuss why such kind of variation happens. At first, I check the structure of thermal tides, because if the thermal tide change, then maybe atmospheric transportation due to the thermal tides maybe change. So to catch such kind of information, I check the structure of thermal tides at maximum period and also minimum period. Minimum period and maximum period. Although the structure is almost same, but maybe detail is a little bit different. For instance, the local peaks of the thermal tide structure are a little bit more clear, I think, in maximum period comparing to the minimum period. And also actually the, how can I say, the amplitude of diurnal tides are double in the maximum period compared to the minimum period. So there should be something in thermal tide structure. So I would like to investigate more in future. 1 minute, sorry, thank you. And also we tested why there is a time lag 100 days. So by checking the GCM result, I'm sorry, I didn't explain detail. We found there could be that, how can I say, time lag, not time lag, the different of response, time scale of response in the zonal wind speed and temperature. In our GCM experiment, temperature always apparently responds later than the zonal wind speed. That could be the nature of Venus atmosphere. Okay, as a conclusion, from Akatsuki data, we found long-term temperature variation. We found long-term variation also in the temperature, and which is interestingly correlates. It shows the correlation with zonal wind speed. It's the one thing we found. Now we are discussing why such kind of this variation happens from combining the observation and also GCM simulation. That's all. Thank you very much.